Okay. So in the last section, we discussed about the diatomic molecule as a harmonic oscillator and anharmonic oscillator, how they will be different in each cases. So in the case of harmonic oscillator, we assumed that the vibration of that diatomic molecule as harmonic in nature, and we have taken the energy levels similar to that of that energy of that vibration of a spring with a spring constant k, or force constant k, which is from Hooke's law, and we have considered initially that particular energy versus internuclear curve, okay? And we have for harmonic oscillator we have EQ spaced energy levels. Okay? So initially we considered it as a harmonic oscillator with this kind of energy that of kr minus r equilibrium. So this is your r equilibrium point. And we have EQ spaced energy levels which are considering this kind of a scenario. And then we considered the realistic case where we have that dissociation energy, that after some energy, after some, if you are providing some energy, then the molecule breaks and the atoms will get separated. And if you consider that realistic scenario, then we have different kind of this energy level, or the energy versus internuclear distance curve will be slightly different. It will be coming something like this. And it will go from here, it will be having this kind of path and go like this. So this is the realistic case. And in the realistic case, we can also see that the equilibrium point of vibration, from the equilibrium point of vibration, the distance is not constant. Okay? So if you are considering the previous case, that is with harmonic oscillation, that with the harmonic oscillation, if you take any point in this curve, any energy level, any vibration, if you consider, so from that equilibrium point, the separation will be same. Okay? So this distance, these two distance, which will be same from that equilibrium point for the case of harmonic oscillator, that red color curve. So that separation, if you take any energy level, if you consider here also, if you consider that distance from that equilibrium separation, and this will be same, is going to be same from that equilibrium. So that the oscillation or the vibration is harmonic in nature, because that from equilibrium point or equilibrium distance or the molecular internuclear distance, if it is in that normal state without compression or without stretching, and with respect to that R value, that bond length, the vibration will be having same distance, which means that if it is stretching, it will be going away from this equilibrium point. If it is compressing, then it is coming close to this zero of this R, internuclear distance. So in that case, we have symmetric fashion. And with respect to our equilibrium, that distance will be symmetric. Okay, that is for the case of harmonic oscillator. But when you are considering realistic case, the molecular vibration in diatomic molecule, if you consider, in that case, your harmonic, the vibration will not be harmonic in nature, and it will be having some slight variation from that, and your oscillation will be anharmonic in nature, and we have some different kind of curve for that. So if you consider this point, for example, this point, for both the harmonic case as well as anharmonic case, we have same kind of distance from equilibrium point of view. And here also we can see that both of these oscillations with the harmonic and anharmonic, they are having same distance from the equilibrium. But when you are considering these energy levels which are higher, okay, in that case we have some difference when you are considering the case with the V is larger. So let's say this case, or you can consider this also. So here we have the vibration which is smaller, or the compression part, we have distance which is smaller as compared to this side. So this is large. So in this case, your molecule will be having some kind of anharmonic oscillation, okay, because the distance from that equilibrium point is not constant while stretching and compressing. So in one portion, in the stretching part, it is having more distance as compared to the other side. So your oscillation will become anharmonic in nature. And in that case, if you are considering energy levels, those energy level will be getting, their energy gap will get reduced. So in this part, the energy level, if you consider this as your first energy level, okay, this is improved curve, and this is your second energy level, let's say. Okay, so there is no difference from that harmonic oscillator because they are having same kind of displacement or distance from the equilibrium point of view. But when you go higher value of V, so let's say this is your V equal to 0, V equal to 1, and if you go for higher values, then your anharmonic oscillator will be having some difference in that distance from equilibrium point, and that will produce some energy difference. Okay? So, and when you go above, which means that for higher value of V, this separation will is getting reduced in each case for the case of anharmonic oscillator. But when you are considering harmonic oscillator, if you are considering that as an harmonic oscillator for your diatomic molecule, then your first energy level comes here, second energy level also comes here. They may not have much difference. But in the third case, you will be having energy level which is with same energy difference from the energy level of V equal to 1 for V equal to 2. This energy gap will be same. And the fourth one will come somewhere here, so that energy gap from V equal to 2 to V equal to 3 also, this energy gap, that will be same, this energy gap also. So that is constant. But when you are considering harmonic oscillator, that is going to be decreased in each case when you are going for a higher value of P. Okay, so that's the overall picture what we have discussed in the last section. And then we have discussed about the relation between the harmonic oscillator vibrational frequency and anharmonic oscillator vibrational frequency in terms of wave number. Then we have discussed the population difference in each state when V equal to 1, 2, 3, etc. What will happen to these populations in those? This means that number of molecules in that particular energy levels, that will be different, and how it is going to vary with respect to temperature, that also we discussed. And we also consider the transition of that particular between that particular energy levels. First, we consider that transition from V equal to 0 to V equal to 1 transition. Okay, so how we will calculate this? Which means in this case we have delta V is equal to plus 1. Is plus 1. Okay, which means that we have to consider this one minus 0. That is 1 minus 0 will become positive 1. So it is allowed. The transition delta V transition rule is delta V equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. So delta V can be plus 1 or minus 1. If it is coming from 1 to 0, V equal to 1 to 0, then it is delta V is equal to minus 1. So we have to take the second state minus the first state. So 0 minus 1 will come as minus 1. That is also allowed. So delta V should be equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. for these are the selection rules for this vibrational transition. Okay, so in first case, we have considered transition from 0 to 1. So in this case, what will happen if you are considering delta E, means delta epsilon, that is the energy in terms of the number. So this is nothing but epsilon at V equal to 1 minus epsilon at V equal to 0. So what is this epsilon at V equal to 1? From the previous expression, I will just show it how it is coming in the first case. So the remaining thing you can calculate. It's a reversal. So in that equation that we have just written for epsilon v, substitute these values of v equal to 1, then we'll get delta epsilon as this will be equal to, first one is v plus half into omega e bar. So it will be like we have this expression ev which is equal to v plus half into omega e bar minus v plus half square times omega e bar xc. This we already discussed in the last section. What is the energy difference between each energy levels? When you consider, sorry, the energy associated with each energy level when you are considering it as an harmonic oscillator. So we have to take this difference between those energy levels. So in the first energy level, we have the energy which is equal to, let's consider V equal to 1 first is. So V equal to 1, that is the highest energy level, minus lowest energy level, we have to take this case. So that will come as V equal to 1 first case. So this is 3 by 2, that is nothing but 1 plus 1 by 2 times omega e bar minus 1 plus 1 by 2 square times omega e bar xc. Okay. So this is the first term for v equal to 1 case, and this has to be taken, this has to be subtracted from this v equal to 0. So this is, second one will come as 0 plus half into omega e bar minus 0 plus half square omega e bar xc. Okay, this bracket is done. So in this case, if you are calculating these values, then we will get in the first case, what is this? 1 plus 1 by 2 is 3 by 2 omega e bar minus 1 plus 1 by 2 square, that will come as 3 by 2 square, that is 9 by 4 omega e bar xc. So this is the first term, minus 1 by 2 omega e bar minus 1 by 2 square, that is 1 by 4 omega e bar xc. The second term. Now, if you consider these values, take these values, then you have 3 by 2 minus 1 by 2 omega e bar in the first case. Okay. So that will come, how much this is? 3 by 2 omega e bar minus 1 by 2 omega e bar. So that will come as 1 omega e bar, right? Then we have minus 9 by 4 omega e bar xc minus minus. So this will become plus. So that will become 9 plus, sorry, 9 by 4 plus 1 by 4 times omega e bar xc bar, sorry, xc. Then it will come as 10 by 4 omega e bar. So as this will come, sorry, this is minus plus will come. So this is minus 9 by 4 plus 1 by 4 will come. So that is 8 by 4. So that is nothing but minus 8 by 4 omega e bar xc. So in total, when you have that transition, that delta epsilon corresponding to this transition, that is from v equal to 1 to v equal to 1 to v equal to 0, this transition. Sorry, I think this is 0 to v equal to 0 to v equal to 1 transition. So in this case, delta E will be equal to, this is nothing but omega E bar minus, this is 1 by 2 omega E bar x. Sorry, this is 2x, 8 by 4 minus 2. So this is 2 times omega E bar. Okay, or I can take this as omega E bar into 1 minus 2x. So this is how it will come, that energy level difference in the transition from 0 to 1. The energy level difference, delta epsilon, that is the energy in terms of wave number. We are not considering delta E here. This is delta epsilon, which is nothing but E energy in terms of wave number in centimeter units. So this is the energy corresponding to that difference from 0 to 1. Now, if you consider a similar transition from 0 to 2, we have delta E, which is equal to 2 omega E bar. I don't know whether I have written 2 in that case. Just check that in the last class, last section. I missed this 2. Anyway, so it is 2 omega E bar times 1 minus 3xc. This much of centimeter inverse. And in the case of v equal to 0 to 3, we have delta epsilon, which is equal to 3 omega E bar times 1 minus 4x. We just check this 2 and 3. I think I have missed that. So this much of centimeter inverse for corresponding to those transitions. Okay, so if your molecule which is going from 0 to 1, this energy level to this energy level, from 0 to 1, which means that what that means, if you are having some molecule here, you are providing some particular radiation that is in infrared region, because we are talking about IR spectroscopy, and molecule will vibrate when it absorbs IR radiation. So this infrared, when it is interacting with this particular molecule, and if this molecule is initially in the V equal to 0 energy level, that is in the ground energy level, ground state energy level, and if this incoming IR radiation is having energy which is equal to this energy gap, okay, the separation between the energy between V equal to 0 and V equal to 1, then this particular molecule will absorb this particular radiation, this IR radiation. Okay. And that is this energy, and that molecule will go to this V equal to 1 energy level state. Okay, that is the transition from V equal to 0 to V equal to 1. In that case, the molecule absorbs that particular IR radiation and goes to the higher energy level. And similarly, here also V equal to 0 to V equal to 2 case, from the ground state, the molecule gets energy which is equal to the 2 times the energy gap between these energy levels. In that case, the molecule will go from 0 to V equal to 2 energy levels. Similarly, for all other transitions. That is the absorption. So actually what is happening here, this is absorption. Absorption of IR radiation by the molecule. Same scenario can happen when you are having the molecule which is already in that V equal to 1 state. Let's say V equal to 1 state. This is in the highest, the higher energy level state, not in the ground state. That molecule can come back to the ground state V equal to 0. Okay, so from higher state to lower state to the ground state. So when it come back, it will emit some radiation which will be equal to this energy of this IR radiation. So this will emit some IR radiation which will be equal to the energy gap or energy level difference between these two energy levels, V equal to 1 and V equal to 0. So in that case, you are getting emission of IR spectrum. Okay. So in this case, we have delta V which is equal to +1. In this case, we have delta V which is equal to -1. One case it is absorbing IR radiation. Second case it is emitting IR radiation. And in both cases, we have the same energy. In one case, it is absorbing that energy. In the second case, it is emitting that energy. If you are studying this kind of phenomena, we have absorption spectra for this kind of for this particular molecule. And we have emission spectra when you are considering this kind of state for transmission. So we can consider different kind of spectroscopic technique. You can measure absorption, transmission, or any other kind of radiations. Basically, it will give you what is the energy difference between these two energy levels when you are probing that molecule with some particular radiation of having some particular energy. Okay, so that is the basic action which is happening in case of this transition. Physically, it will be absorbing or emitting that particular radiation. That is mean by this transition from one energy level to the another next energy. So in reality, what will happen if you are having this molecule? Let's consider we are talking about diatomic molecule now. Whatever we are discussing is about the diatomic molecule. We have not yet discussed about the polyatomic molecule of the for the case of vibrational spectroscopy. So that will be something different. So in the case of diatomic molecule, if you consider this kind of scenario, so this diatomic molecule is having, suppose this is in the equal to 0 state now, that is in the ground state. So it is having some kind of vibration with this molecule. So it is stretching and compressing like that. So that vibrational frequency will be associated with that energy level V equal to 0. That is. And then if you are considering V equal to 1, then this vibration frequency will be fast as compared to previous case when you are having V equal to 1 state. So the vibration frequency, that the stretching and compression will happen very quickly. So per second it will be much higher. Okay, so that frequency, which means that vibration per second, that will be larger when you're having V equal to 1. So if you go V equal to 1, V equal to 2, V equal to 3, higher V value, which means that vibration per second, number of vibrations for that particular diatomic molecule per second will be larger in that case. So if it is absorbing some radiation, it is vibrational frequency increases, which means that number of vibrations per second will get increased. So, and it depends on the energy of the incoming radiation. If it is having enough energy to go to V equal to 5 state or V equal to 4 state, then the vibration frequency will be much higher as compared to the ground state. So ground state, the vibration frequency will be minimum. Then it will go to the higher values as we increase the V value. So these are the transition for V equal to 0 to 1, V equal to 0 to 2, V equal to 0 to 3. We have this kind of energy difference in this transition. And when you consider from that V equal to 0 to 1 case, V equal to 0 to 1 case, in that case we have the frequency of vibration which is almost equal to omega E bar. So this is the frequency that we have, frequency of vibration associated with that particular transition, or the energy difference between those energy levels, which is associated with this particular frequency. And if you consider the second transition, for example, V equal to 0 to 2, in that case, we have the frequency which is equal to 2 omega E, almost, which means that we are not considering this part because XC is this assumption we are taking, like XC is almost equal to 0.01. This is small quantity. So 3xc, 4xc, if you take it, will be some 0.03, 0.04 like that. So we are ignoring this part, 3xc, 4xc. If we are not considering that part, then we will be having this kind of frequencies. So I will just say that with an assumption of xc, which is very small, I can take this one, which is equal to omega E bar, this one, which is almost equal to 2 omega E bar, and this one, which is almost equal to 3 omega E bar. So this is under that assumption that Xc is very small. So it is almost in the frequency range or the wave number range of omega E bar to omega E bar, very close to this value. This one is very small because this one is very small. Okay, so this is omega E bar. That will be the line or the spectral line which will be having the highest intensity. So this one will be omega E bar will be having the highest intensity. That is the line which is near to omega E bar. Okay, and this particular line which is near to omega E bar, which is called as the fundamental absorption. If you're considering that as an absorption, then it is fundamental absorption or fundamental frequency of that particular molecule. And if you consider the other frequencies like 2 omega E, 3 omega E bar, 2 omega E bar, like that, they are called as the first overtone or the second overtone, like that. Okay, so this is your omega E bar. Here, omega E bar, this is your fundamental frequency, or this particular frequency associated with fundamental absorption. If you want to write it, it will be like frequency or the spectral line. I use spectral line because we are talking about the absorption here. We are not talking about the frequency. So I should write it like the spectral line near to omega E bar. Spectral line near to omega E bar, which is called as the fundamental absorption or fundamental absorption peak or line, we can call. And those who are coming near to this 2 omega E bar, 3 omega E bar, these are called as, why I'm talking about near to this omega E bar, because it will be slightly different because of this XC. We have approximated it as 2 omega E bar, but it will not be exactly at 2 omega E bar. It will be less than that, because we have a term which is coming, which is minus 3 XC times 2 omega E bar. So it will be slightly less than 2 omega E bar. So anyway, it is that that line, spectral line, which is close to this 2 omega E bar or 3 omega E bar. These are called as overtones. Okay, and this 2 omega E bar, which is called as first overtone. First overtone frequency. In this case, it is the lines we are considering. This is first overtone, and this is second overtone, and so on. If you consider 0 to 4, 0 to 5, etc., then you have the third, fourth overtone, all those things. Okay. So these are the fundamental line, first overtone, second overtone, like that. And if you consider this in your spectroscopic analysis, then let's say this is your x-axis, this is in centimeter inverse, that is wave number. This is your wave number. So this is in centimeter inverse. So let's say this is your omega E bar position. Okay, and this is your 2 omega E bar position. This is the 3 omega E bar position. So this line, that is V equal to 0 to 1 transition, where it will come? It will come slightly less than that of the omega E bar, slightly less than that. So sometimes it will come somewhere here. Which is very close to this omega E bar, but not exactly at omega E. Okay. And in the next one, that is first overtone, it will come somewhere here. This is also close to this 2 omega E bar, but not exactly to that omega E bar. And in the third case, we have 3 omega E bar. So that is line which is close to this 3 omega E bar. And if you are having 4 omega E bar, we have something like this here also. This is your 4 omega E bar, and so on. So this is for the omega E bar will be somewhere here and less than that. So line which is close to this 2 omega E bar, 3 omega E bar, when you're analyzing the spectra which is coming out from your sample or which is absorbed by the sample if you are analyzing that particular case. So you'll be, when you are considering absorption, you'll be having white or the all other radiations except these particular lines. So in that case, if you are studying absorption band, you'll be having completely white and you'll be having in between some dark bands. Okay, that will happen when you're considering absorption study. If you are considering emission, then we'll be having all other values which are absorbed, which means that we'll be having completely dark in that particular areas. But in at some particular wave number, we'll be having some bright colored bands or lines, and that is corresponding to that emission of particular IR radiation. Okay, so these are the positions of the those lines. And when you consider this particular case, we can see that this line is more intense. This is the this particular line is having high intensity. So this is the high intense line. And if you consider other lines, these are low intense line. This, let's say this is the weak line, and this is very weak. So in each case, the intensity will get reduced. If you consider 0 to 1 transition, that will be having most intense line. Then 0 to 2, if you consider the intensity of those transition will get reduced. That spectral line will get reduced. Why the intensity is going to get reduced? Because the transition will be the most of the number of molecules will be in the ground state, that is in zero state. Okay, so the maximum probable transition or the probable transition or the probability of transition is maximum for 0 to 1 energy level. So the number of molecules which will be going from energy level V equal to 0 to 1 will be larger as compared to other energy levels from 0 to 2, 0 to 3. So when you are having higher V value, okay, 0 to some 10, the number of molecules which will be going from ground state to that excited state level will be smaller. So when the number of molecules is smaller, which means that the number of molecules absorbing that particular radiation is smaller. When that molecules absorb, then only it can go to that V equal to 10 energy level. So molecules will not absorb, number of molecules which will absorb that kind of energy will be smaller as compared to V equal to 0 to 1 transition. If you are giving some energy from 0 to 1, that energy gap, then more number of molecules will absorb that particular energy and go to the first excited state and immediately come back to the ground state. So 0 to 10, the possibility or the probability is less. So that the number, as the number is less, the intensity of those bands with higher V number from 0 to that highest V numbers will be small. Okay. And if you consider the case of HCl, it is which is an example of a diatomic molecule. If you consider HCl, okay, this will be capital. So this HCl, for the case of HCl, if you measure this particular spectra, then it is observed that the highest peak, this one, will come, which is observed at this particular peak observed at around 2,886 centimeter inverse, and the second line, which is observed at 5,668 centimeter inverse, and the third one, this one, which is observed at 8,347 centimeters. Okay, so these lines, which for HCl, which is observed at the high, this high index line, which is observed at 2,886 centimeter inverse. Second one is at 5,668 centimeter inverse, and third one is at 8,347 centimeter inverse. So in each of these cases, if you consider those equations, for example, if you equate this one with that first value, that is omega E bar omega e bar into 1 minus 2xc, and this is equal to 2886. So that is the number corresponding to this fundamental line, the fundamental absorption line, and that is omega a bar equal to omega a bar into 1 minus 2x. That is equal to 2886. From this, we can calculate. Okay, we need the other values also. So omega a bar into 1 minus 3xc. That is, sorry, this is 2 omega a bar, right? 2 omega a bar into 1 minus 3xc. This is equal to 5668. 3 omega e bar into 1 minus 4xc. This is equal to what is that? 8,300. So these are the values which we can get from the experimental analysis of this HCl spectra, IR spectra of HCl with this kind of overtones and fundamental lines. So from this, we have three equations. We have three equations and two unknowns. Xc and omega e bar we have to find out. From this, we can calculate these values. Then we get omega e bar, which is equal to 2,990 centimeter inverse. And then we have this Xc, that is the harmonicity constant of HCl. That will come around 0.017 for something. So these are the, after analyzing the spectra of the HCl, we can get these values, Xc and omega e bar. Okay. And what is the importance of this? If you consider the oscillational frequency, new oscillation, when you're considering any oscillation, then you have this new oscillation which is equal to 1 by 2 pi root k by m if you're having a mass which is associated attached to a spring and it is vibrating, and the spring is having a force constant of k. So in that case, your oscillational frequency will be equal to 1 by 2 pi root k by m. That is the natural frequency. So that is the equation for the frequency of oscillation of that particular spring with spring constant k. So same scenario if you consider for the case of HCl molecule, then we can have this 1 by 2 pi root k by m. Instead of m, we'll be having mu because we are having diatomic molecule. For the diatomic molecule case, we have that reduced mass mu. That is nothing but m1 m2 by m1 plus m2. So from this, we can calculate what is k. K is nothing but 4 pi square. This will be 4 pi square times what is this? New oscillation will come. Then this mu. Right? But what is this mu oscillation? We already know. What is that? Omega e bar. You can say this omega e bar, which is nothing but this mu oscillation divided by c. Okay? If you are considering this in the case of if you are ignoring this xc value, which is very small, and taking these are the lines, okay? An harmonicity constant part we are considering it as a very weak effect, which is very small. Then we can take omega e bar, which is equal to this oscillation, mu oscillation by c, under that assumption that we are having xc, which is very small. So in that case, omega e bar will become mu oscillation by c, or we can say mu oscillation, which is equal to omega e bar into c. Okay. So in that case, this will come as k, which is equal to that oscillational frequency will become, what is that? Omega e bar. I think you have to take square of this, right? And only it will come k. And this, okay. So omega e bar square, c square times v. So this is the equation. This is important. This is equation for force constant corresponding to that particular vibration, which means that in this case, in the case of HCl, it will become as the force constant associated with that bond between hydrogen and chlorine, which means that how much that the bond elasticity, all those things will be depending on this force constant. How much it can stretch, how much it can compress, all those things, how it can do all those vibrations, which will be depending on this force constant. This is nothing from that from Hooke's law. You can consider half kx squared, that k, which is same as this case. So, but in this case, it is the bond, the force constant corresponding to that bond between this hydrogen and chlorine. Okay, this is what we are considering. So, from that we can calculate what is the k or the force constant corresponding to this particular bond. Okay, for each bond we have different bond, this force constant, and depending on that, these vibrations will happen. So from this calculating this omega e bar from the experimental analysis, we can calculate what is the bond force constant corresponding to that particular molecule, and that is the advantage of measuring the or taking the IR spectroscopy of different. In the same fashion, we can also find out what different kinds of physical properties of the molecule by studying this IR spectra. This is one of the examples. Okay? And if you know what is omega e bar, if you know what is force constant, you can also find out what is this mass associated with that molecule. If you are having some, if you are substituting some isotope, and what is, if you want to calculate what is the mass of that isotope, then you have to consider the force constant. If you know that force constant, if you know that omega e bar, then you can easily calculate what is the mass of that isotope that you are going to substitute. Okay, similarly, we can calculate different things. So this, if you are calculating for HCl by substituting this omega e bar value here and substituting the value corresponding to this reduced mass after calculating that mass of hydrogen in the mass of chlorine by mass of hydrogen plus mass of chlorine. And if you substitute all those values, C and everything, then you will get this, which is equal to 516 nm inverse, Newton meter inverse, or Newton per meter. That is the force constant associated with the bond between hydrogen and chlorine in HCl. Now, if you consider another set of transition, like V equal to 1 to V equal to 2 transition, in this case also delta V equal to +1. Okay, these transitions are very weak. This will not happen very, what is said, normally this will not happen. So for this, this is normally very weak. But when temperature increases, but when temperature increases, population in higher energy level increases, and considerable transition may occur. Considerable transition may occur. So what is that means? We already discussed that the number of molecule in any state will be equal to NB by N0. This for example, in this case, it will be V equal to 1 and V equal to 2. We have to substitute those values for V. And if you calculate that, then this will be equal to e raised to minus epsilon V or epsilon 0 of V times hc by kt. That we already know what this is. So in this case, if you substitute uh, values corresponding to this V values, that is, for example, in this case, if you want to calculate V, what is the population at V equal to 1, then you have to substitute this V equal to 1 here. And you have to calculate this epsilon 0 V, that is nothing but epsilon of V equal to 1 minus epsilon of V equal to 0. Okay. So if you calculate what is this difference between these two energy levels in terms of wave number and multiply that with hc by and take that the value 80 and calculate what is that value. Okay. But this is very weak because when you are considering V equal to 1, V equal to 2, V equal to 3 cases, we will be having very less population in that energy levels because at room temperature. But when you are increasing your temperature in this equation, this T is going to increase. This KT in this KT, this T is going to increase. When T increases, this quantity, which is in that exponential term, which will get reduced, and you are taking exponential of some minus of that less value. Okay, so you will get more population. So NV will become uh, exponential. I will just write it as minus epsilon 0 by hc. So when you are t this much times n0, that will come. This is your population. So at any n b equal to 1, you will be having n1. N1 will be equal to e to the power minus e0 of v by hc by kt. So when this t is going to increase, this term in this exponential, which is going to be decreased, and you are taking exponential of minus of that, so which means that your exponential decay rate will be reduced. Okay, then in that case you will get more population, which means that when your temperature increases, your number of molecules in higher energy levels also increases. That's what we have done in the last section. Your this decay will be like this in one case, and your decay will be like this in the second case. And if you consider this as your V equal to 1, you will be having less population here than this, because this is in the 1000 Kelvin, this is in 300 Kelvin. So as compared to 300 Kelvin, that is your temperature is at room temperature. If you are increasing that temperature into 1000 Kelvin, your number of molecules will be getting increased to this point. Okay, so when you increase the temperature, when you have having temperature which is high, then your population at V equal to 1, V equal to 2, V equal to 3 will start to increase. Still the population, that is number of molecules in the energy level V equal to 1 will be larger than V equal to 2, which will be larger than V equal to 3, etc. That is that exponential. From that exponential you can see, even if 1000, if it is 1000 Kelvin, V equal to 1 will be having more population than V equal to 2. Okay. So anyway, so V equal to 1, if you are considering at room temperature, number of molecules at V equal to 1 energy level or the higher energy level will be small. But when you increase the temperature, number of molecules in V equal to 1 or any higher energy levels will get increased with increasing in the temperature. And in that case, V equal to 1 to V equal to 0 transition, V equal to 1 to V equal to 2 transition, that can be possible. Okay, so when you increase the temperature, number of molecules in V equal to 1 state will increase, and the transition from V equal to 1 to V equal to 2 may occur, can be possible. So in that case, this is happening because of the increasing of this temperature. In that case, we'll be calling this kind of transition as hot bands. And these kind of transitions are called as hot bands. So if you calculate what is the difference of energy level in this particular transition from V equal to 1 to V equal to 2, so that delta epsilon, if you calculate by using the aforementioned formula, So you substitute V equal to 1 and V equal to 2 for that. So your second state is 2. So you have to take difference between these two. Substitute V equal to 2 in the first case for that EV equation and calculate what is the corresponding expression. Substitute V equal to 1 in the second case and take difference between those two energy levels by using that previous equation that I just explained. Then we will get delta E, which is equal to omega E bar into 1 minus 4x. So this will be omega E bar into 1 minus 4x. This much of centimeter inverse. Similarly, you can consider what is the next energy. For example, 2 to 3. You consider 2 to 3, 3 to 4. All those you can consider. Then you have different number of hot bands which will also be present in your spectrum. So in this particular case, we will be having omega E bar into 1 minus 4xc. Okay. So this hot, so this kind of weak absorption are known as hot bands. Hot bands. Why it is hot? Because it will happen only when your temperature is high enough. Okay, in a some enough value, then only you will be having population at V equal to 1, V equal to 2, etc. Higher energy levels. Then only this V equal to 1 to V equal to 2 transition will happen. If there is no molecule at V equal to 1, then that kind of transition will never happen. But when you increase the temperature, number of molecules in V equal to 1 will be comparably higher. And in that case, that molecule can go to V equal to 2 state. Okay, that is possible. So V equal to 1 to V equal to 2 is possible. So that transition is possible. So V equal to 0 to V equal to 10 transition directly, that is not possible. Don't confuse with that. Directly from 0 to 10 is not possible because your selection rule delta V will be equal to plus or minus 1, plus or minus 2, plus or minus 3. So in this case, it is possible, but it is rate. If you consider that rate, it will be very small. What will be that delta V for 0 to 10? 0 to 10, if you consider, that will be plus 10. Okay, that selection will be so that can be possible. But the population, if you consider from that transition from 0 to 10 energy level, that is very big. In between you have V equal to 2, V equal to 1, V equal to 2, V equal to 3. So the molecule always try to have these energy levels. Anyway, the molecule will try to come to the ground state in all the cases. So if you are providing enough energy, then only it will go to the higher energy levels. And if you are having higher temperature, and the temperature is higher enough, then you can have the molecule which is in the excited state energy level. Then from 1 to 2, 1 to 3, or 2 to 3, 2 to 4, etc. Those transitions are also possible. Such transitions which are called as hot bands. So what will be the position of this band in the last diagram? For example, if we consider this kind of diagram, so this is omega E bar. So this is omega E bar. So this, what is this? This is omega E bar. We are considering first one, omega E bar into 1 minus 2x, right? So this is almost near to this omega E bar minus omega E bar times 2x. So that is this first line. So that is very intense. But when you consider the overtone corresponding to that, that will be first overtone. Not overtone. First hot band, if you consider that hot band from 1 to 2 level, that will be equal to omega E bar into 1 minus 4xc that we just discussed. So that will be coming very near to this omega e bar, but less than that value, because here first overtone, first fundamental line we have here 2xc, that is omega e bar into 1 minus 2xc, but in this case we have 1 minus 4xc. So very near to this, we have the this hot band, very near to this, but less than that. But the intensity wise, it will be very weak. The hot band position will be somewhere here, but intensity wise, it will be very weak because number of molecule in vehicle one state will be smaller. Okay? So intensity wise, it will be, if you are considering second hot band, fourth, third hot band, all those things, then the intensity will be very small. It is very weak to observe. Okay, so that's about the hot bands, which will be also which also will be present in this spectra of this one. Now, if you consider the case of diatomic molecule, what we have discussed so far is pure vibrational spectra, but that is not the case. The diatomic molecule will always have vibration as well as rotation. Okay? So we'll consider here diatomic molecule with both vibration and rotation. And rotation. And we call this as diatomic vibrating rotator. So we have both vibration as well as rotation, and it is a diatomic molecule, which is called as diatomic vibrating rotator. So, for example, if you consider the energy separation of different molecules, then if you consider the case of rotation, for rotation case, okay, for rotation case, we have the energy separation in wave number we are saying. So the energy separation is nothing but in the order of in the order 1 to 10 centimeter inverse. For rotational spectra, it will be in the 1 to 10 centimeter inverse. Within that range of energy separation will be there for each energy levels. But in the case of vibrational spectra, for the vibration, if you consider, this energy separation will be in the order of around 3000 centimeter inverse. For example, if you consider as HCl molecule, we have observed that which is around 3000 centimeter inverse. We just calculated that here, and it is found that it is coming around 3000. So it is coming around 2990 centimeter inverse. So the vibrational frequency is much higher, which is having the energy level difference for the vibrational spectra, or spectroscopy, which is much higher than that of the rotational energy separation. So this separation is 1 to 10 centimeter inverse, but this is around thousands of centimeter inverse that separation will come. So as compared to the rotational energy levels, the separation between energy levels will be much higher for the case of vibration. Okay, so in this case, we can treat these two different uh, energy levels separately. Okay, so as the energies of these two motions are so different, we can treat these two uh, motions separately, or assume that the rotation and vibration happens independently. So because of this, as the energies of two motions, which means that vibration and rotation motions are so different, so different. We can assume that rotation and vibration happens independently. Okay? Because their energy levels, energies are very different. We are treating this vibration and rotations which are happening so independent. They are happening independent. And this particular assumption is called as von Oppenheimer approximation. So since the energy level difference between the rotation and vibration cases are so different, the energies are very different. One is in the range of 1 to 10 centimeter inverse, another one is in the thousands of centimeter inverse. So they are very different. We are treating the vibrational motion and rotational motion independently. And this kind of assumption, which is called as von Oppenheimer approximation. And in this case, we are considering total energy, which will be equal to the sum of vibrational energy and rotational energy. So E total will be equal to E vibrational or E rotational plus E vibrational. Similarly, epsilon total, that is energy in terms of wave number, will be equal to epsilon rotation from epsilon vibration. So what will happen to this total energy in terms of epsilon? So epsilon j comma v, that is rotational quantum number comma vibrational quantum number, that will be equal to v into j into j plus 1. I will remove this bracket. So this will be equal to v into j into j plus 1 minus d into j square into j plus 1 square. This is from that higher order terms. Okay. And we are considering only that much, and this has to be added with the vibrational phase. So this will come as plus u plus half into omega e bar minus this put one plus half square omega e. Uh, so this is the total value of epsilon. Now, if you are not considering that d, this we are considering this d value, which is very small. If you consider like that, in that case, this epsilon j comma b, this will become b times j into j plus 1 plus b plus half times omega e bar minus plus half square. I think the just check this expressions, which is like equal to For vibrations, we have epsilon v, which is equal to v plus half into omega bar minus v plus half into square omega bar. Okay, that's good. We have that x also here. So only that two terms we are considering, and we are ignoring this term. Okay? In that case, we are having this kind of, we'll be having this kind of. Okay, now means that we are not considering, in this case, we are not considering that centrifugal distortion constant. This will be from that centrifugal distortion constant d we have taken, which is approximately equal to 0. This means that it is comparatively very small under assumption. This assumption we have taken, and in that case, it will be like b into j plus 1 plus b plus half omega bar minus plus half square omega bar. In other words, we can say whatever we are having that vibrational energy levels, that has to be added with this b into j plus 1. That is the total energy level. Okay. So what will happen to this energy level diagram in this particular scenario? If you are drawing that energy level diagram, so take that internuclear distance and dissociation energy, all those things. So it will be having a spectra like this. This is your internuclear distance R, and this is your energy. So we'll take that at epsilon, which is in number. So let's consider a small portion of that energy level, that lower part. So it will be coming like this. We'll be touching at that. So we are considering that lower energy, v equal to 1 and v equal to 2 state only. So what will happen to this? Consider this is your v equal to 1 state. That's right. And then we have that v equal to 2 state somewhere here. This is v equal to 1. This is v equal to 2. So in each of these states, we have this v equal to 1. If we substitute, what will be the value of this quantity? We have to calculate. Okay. And what is the value of v when we are substituting v equal to 2? And corresponding energy, we are having this. Equal to 1. And this is when your j value, which is equal to 0. This is when your j value is. Now I'm considering this j, which is j double dash, and this one is j dash. So j dash is nothing but the rotational energy quantum number, corresponding to the vibrational state v equal to 2. And j double dash is the rotational quantum number corresponding to v equal to 1. Now, if you consider the cases when your j equal to 1, 2, 3, etc. So our v is fixed. So here v is fixed. V value is equal to 2 and j equal to 0. Now what we'll calculate? We'll calculate what will happen if your v equal to 2, but your j is going to be different. J equal to 1, j equal to 2, etc. What will happen in that scenario? So when your j is different, okay. So when your j equal to, we already calculated what is this b into j plus 1. When we talk about this, when we discussed about that rotational spectra, we calculated this. When your j equal to 0, this will be 0. Along with that. Okay, so when your j equal to 0, let's say j equal to 0, this quantity will become 0. J equal to 1, when your j equal to 1, this quantity will become b into 1 into 1 plus 1, so it will become 2b. Then your when your j equal to 2, then your b into 2 into 2 plus 1, that is 3 into 2, 6b. And when it is 3, it will become 3 into 3 plus 1, that is 3 plus 1 is 4, 4 into 3, 12b, etc. So each time your energy level will be increasing. That the difference between energies, in this case it is 2b, in this case it is 4b, here this will become 6b. So each time energy level difference is becoming large. So when your j equal to 0, this term will not be contributing to the total energy level, because this term will become 0 when your j equal to 0, and only this part will be there. So your v equal to 2, when your v equal to 2, you will be at the same position when you are having that vibrational energy, because rotational energy will not affect because j equal to 0. But when your j which is equal to 1, let's say j dash that is equal to 1, in that case you will be having some energy level which is higher than that of v equal to 2, because you have to add that b into j into j plus 1 with that vibrational energy level. So we have energy level here. And in the next case, we have energy level number here, because in each time that energy level gap will be getting increased. As you can see here, 2b, 6, 4b, 6b, that energy level gap is getting increased. So because of that rotation, we have this kind of energy level. Similarly, here also we have j dash, j double dash is equal to 0, then we have j double dash is equal to 1, and j double dash which is equal to 2, j double dash which is equal to 3, and so on. So in each case, it will be getting increased. Okay? So this is a rough diagram. These energy levels will be very close, and this V, this difference will be very high. Okay? So don't think that this will interact with this one very soon. Okay? That is not going to happen. It is the gap is very high. If you want to draw that exactly, so this will be, so this is a kind of a diagram that you can understand how it is going to vary. But in the realistic case, it will be looking like that. If you are looking for a realistic scenario, and if you consider your V somewhere here, V equal to 1 here, and your V equal to 2 somewhere here, and that rotational energy levels will be coming very close to this. This will be the first one, this will be the second one, this is the third one, this is fourth one, this fifth one, and so on. Okay. So they will be very close to this V1, V equal to 1. So in reality, if you take hundreds of energy level, it will be reaching somewhere here. Similarly, here also we have very close to this number of energy levels, which is coming from that rotational, because of that rotation of the molecule. So the energy level which will be still close to this V equal to 2 case, and don't think that this is going to interact with this energy very easily. So it will take number of energy levels or J value which is very high to reach at that point, because the energy level difference between these two, this rotational energy level, that is around 10 centimeter inverse. But these two, if you are considering, these two energy level, if you are considering, that is in the 1000 order. This energy level will be having some 10 thousands of order. In the case of HCl, it is around 3000 centimeter inverse. But in the case of rotational energy level difference, difference between these adjacent energy levels, if you consider, that will be in the order of 1 to 10 centimeters. So you need around hundreds of energy levels in between these two vibrational energy. So there will be hundreds of rotational energy levels in between these two vibrational energies. Okay, so don't think that this is the exact scenario. It is going to interact with this very easily, but between these two energy levels, these two vibrational energy levels, there will be hundreds of rotational energy levels. Okay, so that's about the case when you are having both rotation and vibration. They are acting independently. So the energy level will be looking like this. Now, if you are considering that transitions and corresponding selection rules, what will happen to those selection rules in this case? Selection rules for this case, that is for a vibrating rotator, diatomic vibrating rotator. Then we have delta V equal to plus or minus 1, plus or minus 2, plus or minus 3, etc. as usual. And along with that, we have delta J, which is equal to plus or minus 1. And if you substitute this for a particular case, we'll just go up. So if you substitute that in the delta EJV value, so epsilon JV, we have epsilon J comma V, which is equal to this we already discussed, B into J plus 1 plus V plus half V plus half into omega E bar, minus V plus half square omega E bar. Now, if you take the difference between energy levels, two energy levels, for example, delta epsilon, for example, in this case we have J dash comma B equal to 1 minus that is the that is the energy level difference between those energy states, delta J dash B equal to 1, and the second case will be epsilon J double dash, that is higher rotational energy level, comma B equal to 0. Sorry, J double dash is the lowest one, lower one. So this is the delta epsilon. This is equal to that. And what will be this quantity? This will be equal to V into J dash into J dash plus 1 plus, in the first case, V equal to 1. So it will come as 1 plus, this term will be coming as 1 plus 1 by 2. This quantity is, first one we are considering equal to 1, so 1 plus 1 by 2 times omega E bar minus, what is this? This will also come as 1 plus 1 by 2. Equal to 1 plus 1 by 2 square omega E bar T method quantity. This quantity minus V into J double dash into J double dash plus 1. I will take this as another bracket. Plus V equal to 0 means half omega E bar minus half square, that is 1 by 4 omega E bar T. So if you calculate these values, then we'll get delta epsilon j comma v, which is equal to omega e bar into 1 minus 2 xc plus b into j dash minus j double dash into j dash plus j double dash plus 1, this much of centimeter. Or we can also say delta epsilon j comma v will be equal to omega 0 bar. Don't confuse with that previous omega 0. This is omega e bar into 1 minus 2x. So this plus b into j dash minus j double dash into j dash plus j double dash plus 1. You just subtract these two values and we'll get it. Okay, this much of centimeter inverse. So this is the energy level difference. So omega e bar, omega 0 bar is nothing but omega e bar into 1 minus 2x. So that is omega 0 bar. So this is the energy level difference when you are considering this vibrating rotator. So there we have both vibration and rotation, and between each rotational quantum numbers. So the difference between those energy levels will be omega 0 bar plus b into j dash minus j double dash into j dash plus j double dash plus 1 in between. So this is the omega 0 is omega 0 bar is omega e bar into 1 minus 2x. So your energy level difference will be like this. So you can consider two cases here, two different scenario. First case is when your delta j equal to plus 1. When delta j is equal to plus 1. What is that means? Delta j means the difference between quantum numbers j dash and j double dash. So j dash is the highest rotational quantum number minus j double dash. That j double dash is the lower quantum number, rotational quantum number. So this will be equal to plus 1. With this we can also say j dash is equal to j double dash plus 1. That is delta j. So this is your delta j, j dash minus j double dash. That is equal to plus 1. Then what will happen to your delta epsilon j comma v? That will be equal to omega 0 bar plus j dash minus j double dash. This is 1. Okay. Again you have j dash plus j double dash here, this quantity, j dash plus j double dash plus 1. Okay. So what will happen to this? This will become when you are considering your for example this quantity j dash plus 1 is here. So this will become like 2b times j double dash plus 1. So that is the delta j for the plus 1 case. And in the second case, we have delta j, which is equal to minus 1, means that j dash minus j double dash, which is equal to minus 1, or j dash equal to what will be that? J double dash minus 1. So in this case, what will happen? Delta epsilon jv, that will become omega 0 bar omega 0 bar omega 0 bar minus 2b into j prime plus 1. there you have j prime minus j double prime. So this quantity, in this case, this quantity will become minus 1. Okay? So minus 1 times this quantity, that will become j prime plus 1. That is, here it will come 2 times that value, because your j double prime is j prime plus 1. This is easy. This is j double prime will be equal to j prime plus 1 here, under this condition. J double prime equal to j prime plus 1. Substitute that in here, then you will get j double prime. Instead of this j double prime, it will become j prime plus 1. Again, one more j prime plus 1. So 2 times j prime plus 1 will come. So we will get 2b times j prime plus 1. And this minus is coming from j prime minus j double prime. This is equal to minus in this case. Similarly, in the previous case also, if you substitute j prime equal to 1 plus j double prime, then you will get 2 times 1 plus j double prime. So 2b into j double prime plus 1. So this is the two scenarios. These are the two scenarios which we can have. So if you are taking it as in general, okay. So these two expressions, can be conveniently combined as, in that case we will be having delta epsilon j comma b, which will be equal to omega 0 bar plus or minus 2b times okay, j prime we cannot write, so can write it as 2b times some other constant, some other value which is equal to m. So omega e bar plus or minus 2b times m. So where m equal to, where m equal to where m equal to plus or minus 1, plus or minus 2, plus or minus 3, and so on. So this much of centimeter. And m is positive means, m is positive. What is that means? M is positive means delta j is positive, and delta j is positive. M is positive. If you are taking m value as positive, then that means delta j is positive. So, and if you are taking m as negative, then delta j is negative. So, for m is negative, delta j is negative. So, delta j is positive means what? Delta j is positive means your m will be equal to j double prime plus 1. In this case, what will happen? Your m will be equal to j prime plus 1. So that is the convenient method representing both those equations in a single equation, in a single expression. Okay, and remember that m will never become 0. M will never become 0 in this case. So this frequency omega 0 bar, which is known as the band origin, this omega 0 bar is the band origin. Okay, so delta j or omega 0 bar, which is called as band origin, and the delta j, which is equal to plus 1, that is corresponding to this case, plus 1 or positive value. I should write this as positive, delta j, which is positive, that is corresponding to R branch. They are called as R branch. Delta j is equal to positive, which is called as R branch. Whatever value of you are taking for delta j, which is positive, is an R branch. And delta j, if it is negative, then it is called as P branch. So basically there are three branches or three spectra we'll get. One is band origin, that will not be having any spectra at band origin this time. So basically there are two branches. One is R branch and second one is P branch. In this particular case, we have R branch and the P branch. Okay. This all these calculation up to this we have done without that centrifugal distortion constant D. We have considered D value which is very small and which is approximated to 0. If we consider that centrifugal distortion constant, which we discussed in the rotational spectra, so constant, include that with this expression, then your delta epsilon j comma v will be like omega 0 bar plus qbm minus 4dmq. Will be like this, and this qbm and the values of b are as mentioned in the earlier. When you are including this distortion constant, centrifugal distortion constant, so this much of centimeter inverse. Now, if you are looking, what is the spectra of this particular one look like? So we are talking about this energy level. I think it's not that much visible. Okay, here it is. So if you consider this diagram, which is corresponding to this diagram, if you look, you can see that these are two states, two scenario when delta j equal to -1 and delta j is equal to this is delta j equal to -1, this is delta j equal to +1. And if you consider different vibrational state, here we have v equal to 0 here and v equal to 1 here. Okay, v equal to 1. So these are the state which is corresponding to that v equal to 1. These are the state which is corresponding to v equal to 0. Then we can see for j double dash equal to 0, 1, 2, 3, 4, etc. We have different energy level. Similarly, we have j dash equal to 0, 1, 2, 3, 4, etc. We have different energy levels. So the transition will happen in such a way that delta j, in this case, remember delta j should be equal to plus or minus. Okay, that is the transition or the selection rule. So in this case, we can go from, and also delta v can be plus or minus 1, plus or minus 2, etc. So if you are considering delta v as plus or minus 1, in this particular case, we are considering delta v equal to plus 1 and this selection rule for delta j. Which delta v equal to plus 1 means we are going from v equal to 0 to v equal to 1. Okay, that's why you are putting delta v equal to plus 1, and delta j is there can be plus or minus 1. So it can go from j equal to 0 to j equal to 1 state. This is j equal to 1 state and this is j equal to 0. Okay, so 0 to 1 it can go, from 1 to 2 it can go, from j equal to 2 to 3 it can go. In all these transitions, your delta j equal to plus 1. Okay, if you are taking the difference between the higher and lower state, in this case we have 1 minus 0. In this case we have 2 minus 1. In this transition, if you consider, we have 3 j equal to 3 here, j equal to 2 here. So 3 minus 2 is 1 plus 1. So all these transitions correspond to delta j equal to plus 1. But in this case, we can consider we are going from j equal to 1 to j equal to 0 state. here this transition that is coming from 0 to 1, this transition. Okay, so in that case, it is going from 1 to 0. It is going from 1 to 0. Here we have 1 energy level which is equal to 1 and to 0. So in that case, delta J is 0 minus 1, that will become minus 1. To consider this transition, for example, another transition. So in this transition, we have 3 here, the J value is 3. Here we have J value which is 4. So your transition is from, you have to take the J value which is the highest energy level is J dash and the second one is J double dash. So you have to subtract from higher energy level to lower energy level. So we have to subtract 3 minus 4. We have to do 3 minus 4. In that case, you will get delta J which is equal to minus 1. So for all these transition, delta J which is equal to minus 1. Delta J equal to minus 1. And all these transition we have delta J equal to plus 1. Okay. And whatever the transition we have delta J equal to plus 1, we have R branch. And whatever transition we have for delta J which is equal to minus 1, which are P branch. So we can have the central one, that is the band origin. We have omega 0 bar here, this one. Then we have R0, R1, R2, R3, etc. Different bands here. You can see that R branches. This is the R branch. And if you consider P branch, these are the P branch. Okay, this is P1, P2, P3, and so on. And remember, we have R0 here, then R1, R2, R3, etc. But we are not having P0. We do not have P0, but we have P1, P2, P3, P4, etc. Okay. So that's about the vibrational or vibrating rotator case. And we have the carbon monoxide spectra that we'll discuss in the next class. So up to this, we have covered up to this vibrating rotator with Born Oppenheimer approximation. And in the next class, we will discuss something like breakdown of this Born Oppenheimer approximation and what will happen in that case. So this is the spectra as corresponding to this vibrating rotator. In this spectra, we have 2 branches. One is P, one is another one is R. So if you are looking at this spectra, you will be having something like this. Here also we will be having some different lines like this. So this branch is consist of these R's, and this branch is consist of those P lines. And fundamentally, we have omega E bar here, that is the band origin, and this is corresponding to delta J is positive, and this is corresponding to delta J is negative. This branch. So that's about the spectra of vibrating rotator, diatomic vibrating rotator. Yet we are not going to, we didn't discuss anything about the polyatomic case. We are only considering that diatomic case. Okay. And later we will discuss what will happen to those cases when we have different molecular geometry apart from the diatomic molecule. What will happen if polyatomic molecule, if you are considering linear polyatomic molecule? What will happen if it is not linear, which means that if it is, for example, some symmetric top molecule, like that case, what will happen to this spectra, vibrational spectra? So those things we will discuss in the upcoming classes.